everyone, my name is Dr. Aradhna Sahu, Associate Professor, Computer Science and Engineering Department from Shri Santosh Rungta Group of Institution, Rungta College of Engineering and Technology, Bhilai, Chhattisgarh. Welcome to today's lecture on the intriguing topic of steganography and the innovative steganography tool that has taken this ancient art to new heights. I am thrilled to guide you through this journey of hidden messages, digital concealment, and the fusion of technology with artistry. So let's start the lecture. As the name suggested, image steganography refers to the process of hiding data within an image file. The word steganography is derived from two Greek words, stagos and graphia. Stagos means to cover and graphia means writing, thus translating to covered writing or hidden writing. Steganography is a method of hiding secret data by embedding it into an audio, video, image or text file. It is one of the methods employed to protect secret or sensitive data from malicious attacks. Some examples of steganography includes: first, writing the invisible ink. Second is embedding text in a picture. For example, an artist hiding their initials in a painting they have done. The third example is backward masking a message in an audio file. Do you remember those stories of evil messages recorded backward on rock and roll records? Next is concealing information in either metadata or within a file header. The next is fifth is hiding an image in a video viewable only if the video is played at a particular frame rate, and embedded a secret message in either the green, blue or red channel of an RGB image. So these are the various examples of image steganography. Let us understand first how it is differ from cryptography. Cryptography and steganography are both methods used to hide and protect the secret data. However, they differ in the respect that cryptography makes the data unreadable and hides the meaning of the data, while steganography hides the existence of data. Now we understand how is steganography done. Since the computer description of an image contains multiple bits, images are frequently used as a cover source in digital steganography. The various terms used to describe for image steganography that are: first is cover image. It is a unique picture that can conceal the data. The next is messages, real data that you can mask within picture. The message may be in the form of standard text or an images. The next is stago image. This is an image with a hidden messages. Then stago key. The message can be embedded in cover images and stago images with the help of a key, or messages can be derived from the photo themselves. Let's discuss the principle of steganography. Actually, how is it done? As we all know that an image is represented in terms of matrix as n cross m in case of grayscale images, or n cross m cross 3 in case of color images matrix in memory, with each entry representing the intensity value of a pixels. In image steganography, a message is embedded into an image by altering the values of some pixels which are chosen an encrypted algorithm, and the recipient of the image must be aware of the same algorithm in order to know which pixel he or she must select to extract the messages. The image selected for this purpose is called the cover image, and the image obtained after the steganography is called the stago image. The process of image steganography is shown in figure 1. And the detection of message within the cover image is done by process of staganalysis. These can be done through comparison with the cover image, histogram plotting, or noise detection. So, a steganography techniques involves hiding sensitive information within an ordinary and non-secret file or messages so that it will not be detected. Let us discuss the various types of image steganography methods. These can be categorized in various domains such as spatial domain and also in transformed or frequency domain. In figure 2, we can see that the various methods of image steganography. Here we can see first spatial domain techniques. In these techniques involves direct modifications on the pixel value. The techniques like histogram modification, pixel value differencing, and age-based method can be used for spatial domain steganography, whereas the transform domain frequency work on the transform domain coefficients that are obtained. These methods involve applying a transform to the image, for example wavelet transform, and then embedded the secret message in the transformed coefficients. On this lecture, we will explore two main methods in spatial domain steganography. They are LSB, least significant bit, and Fibonacci methods, and other three methods under transformed domain. They are DCT, discrete cosine transform, DWT, discrete wavelet transform, and DFT, discrete Fourier transform methods. Let us understand one by one. We will start from first method, that is LSB. The LSB steganography, we know that the group of binary bit we have least significant bits and most significant bits. The LSB stands for least significant bits. Let's see an example. In this example, as shown in figure 3, we know there are multiple bits where here this 1 and this 0 are most significant bits, and this 1 and this 0 are least significant bits. In this example, I am going to take the last 2 bits as the least significant bits. Now, what I am going to do with these least significant bits? So, that is what the main theme of least significant bit steganography. Say, if we have an image and this image will be having a lot of pixels where every pixels will be having a color. So, and this image may be following any color model. Let's take the images following a color model, which is RGB color model, the red, green and blue color model as shown in figure 4. Using this color model, we can get any color. If we want to red color, how red color is generated using this RGB color model is that this function is going to take three parameters. The first parameter is red parameter, the second parameter is green parameter, and the third parameter is blue parameter. There is a pixel, and if that pixel is having the value RGB of 25500, it means that pixel will be highlighted in red color. How did we get this? So, a total of 24 bits are there for every pixel, which is following RGB color model. Out of these 24 bits, the first 8 bit for red color, the second 8 bits for green color, and the last 8 bit are for the blue color. If the red color parameter is having all ones in binary, in decimal, if it is all 255, or in binary, if it is all 1, and we don't have any set in green color and blue color, then this pixel will be highlighted in red color. How green color is generated? In the RGB color model, the red parameter will be 0, the green parameter will be set, and the blue parameter will be 0 in binary. RGB of all zeros in the first half, all ones in the second parameter, means the green color is set, and all zeros in the third parameter means the blue color is not set. So, the pixel which is having this color value will be highlighted in green color. Similarly, for getting the blue color in the RGB color format, the red parameter will be 0, the green parameter will be 0, and the blue parameter will be set as in decimal 255, or in binary all ones. Then using these, when we get multiple combination of colors, the RGB of 100, 0, 10 will give some other color. The RGB of 200, 265 will give some other color. So, you can adjust the value of the RGB color format in order to get appropriate color. Please be noted that parameter is going to take a value from 0 to 255. Now, this is the idea behind the LSB steganography. In order to understand these clearly, I will show you an example. Now, please watch this example in figure 4. What's the color of these two boxes? It's green color, right? Do you believe that both the green color are one or and the same? Let me show you. Actually, in this color representation, there is no red color field which is set. So, all bits in red parameter is 0 and green parameter are set as 255. It means all bits are 1 in green parameter, and in the blue parameter no bits are set. So, it's purely a pure green color. But if you come to these, can you see here the red parameter is not set like the previous case? The blue parameter is also not set like the previous case, whereas here is the green parameter. Can you set instead of 255, I am using a value 252. It means the last two bits are not set. It means this is also represent in green color only. But if you note here, these two bits are the least significant bits of green parameter. So all pixels in the second box are with the R value 0, green value 252 and B value 0. It is also a green color. But there is a difference between first case and the second case. So it's clear that we are going to reserve the least significant bits for hiding the data. In this example, we are going to reserve 2 bits. These 2 bits can be in red parameter, blue parameter as well as in the green parameter. But in this example, I am just showing that I am going to reserve only these 2 bits in green parameters only. So that we can do with these 2 bits is that we can make use of these 2 bits for storing our information, so that the image seems to be the same image, but there are hidden messages in these 2 portions. Or we can also observe the 2 bits in the red parameter as well as in the blue parameter, so that we can store our information in these places. And that's why the steganographic techniques which involves these idea is called as least significant bit steganography or simply LSB steganography. Before we see a sample image, I wanted to repeat, we can use LSB of every pixels. Let me show you an example. In this example, can you see figure 5 for images of Rungta College that I am projecting? This is the first image and this is the second image. This is the image without hidden information and this is the image with hidden information. No one can understand that there are hidden information in this image. You know why? In the original images, what we are going to do? We are going to remove least significant bit from the R part, G part and B part, and we are going to place our information's binary bit in these places, so that this image seems to be like the same image with little modifications. No one can understand that if hundreds of images are given to the users and he can't be find which image has which hidden information. The second category under spatial steganography is Fibonacci methods. Fibonacci sequence based steganography is a technique that involves hiding information within the Fibonacci sequence to achieve a form of data concealment. Figure 6 illustrates the principle of Fibonacci based steganography. At first, the image pixel's value is represented in Fibonacci presentation. A secret bit is then embedded into the Fibonacci sequences by LSB algorithm. Finally, the Fibonacci sequence with secret bit embedded is covered to binary domain before being returned to stego image. Here are the steps to perform Fibonacci spatial domain steganography. The step 1 is understanding the Fibonacci sequence. It is a series of numbers where each number is sum of two preceding ones, usually starting with 0 and 1. So, the next number is 0 plus 1 equal to 1 and the another next number is 1 plus 1, that is 2 up to n terms. So, The final series of sequence of the Fibonacci series is 0, 1, 1, 2, 3, 5, 8, 13 and so on. The step 2 is convert information to binary. The conversion the information you want to hide into binary format. These could be next and image or any other form of data. The step 3 is choose a set of Fibonacci numbers. These numbers that will act as indicates in the sequence. These numbers will represent the positions where you will embed the binary data. Step 4 is embedded binary data. Starting with the first Fibonacci number in your chosen set, find the corresponding position in the Fibonacci sequence, replace the value at the position with the first bit of your binary data. Now, move on to the next Fibonacci number in the set and replace the value at the position with the next bit of your binary data. Continue this process until you have embedded all the binary data. Step 5 is store modified sequence, which now contains your hidden binary data. Make sure to keep track of the original sequence as well. It is important to note that Fibonacci based steganography is not a very secure technique and it's relatively easy to detect if someone knows what to look for. Additionally, embedding large amount of data can distort the Fibonacci sequence significantly. Now we are moving towards second category of image steganography is frequency or transform domain steganography. In this section, we will discuss three different methods: DCT, DWT and DFT. Let's start with DCT first. DCT means discrete cosine transform steganography. In this method, the secret message is embedded in the frequency domain coefficient of the image using the DCT transformation, which is commonly used in JPEG compression techniques. Altering these coefficient slightly can hide the information while maintaining the image's visual appearance to some extent. Figure 7 shows the complete steps of DCT steganography. Here are the steps involved in using DCT for steganography. The step 1 is image selection. Choose the cover image in which you want to hide the secret information. These could be any image in which you wish to embed the data. The second step is block division. Divide the cover image into smaller blocks or segments. The common block sizes are 8 cross 8 blocks. Each block will be processed individually for steganography. The step 3 is DCT transformation. Apply the 2D DCT to each block. This involves converting the pixel values in each block into their corresponding frequency domain coefficient. The top left coefficient, DC coefficient, represent the average color and the intensity of the block, while the remaining coefficient, AC coefficient, capture the finer details. The step 4 is now quantization. Divide the density coefficient by a quantization matrix. The quantization process reduces the precision of the coefficient and allows for the hiding of data in least significant bits of the coefficient. The quantization matrix plays a key role in the strength of the steganography methods. The step 5 is data embedding. Modify the least significant bits of the quantized density coefficient to encode the secret data by replacing the least significant bits of the coefficient with the bits of the secret data. You can hide information within the image. Care must be taken to ensure that the changes are not too obvious to the human eye, and the extracting message from a stego image is just the reverse process of hiding the information, as we see in the figure 6. Now we will discuss next method is DWT steganography. It is also known as discrete wavelet transform steganography. It is a technique used to embed secret information within digital images using discrete wavelet transform. This technique is a mathematical transformation which is used to decompose an image into multiple frequency components, each representing different level of detail. It works by modifying the least significant bit of the wavelet coefficient in the transformed image. The LSBs are bits in a binary number that have the least effect on the overall value of that number. Therefore, replacing or modifying the least significant bits has minimal impact on the visual quality of the image but can be used to hide secret information. Let's we look a general outline of how DWT steganography works. The step 1 is image transformation. The cover image is transformed using the DWT to generate approximation and detail coefficient at different levels. These coefficient represent different frequency component of the image. Step 2 is embedding. The secret information is encoded as binary data. The LSBs of the wavelet coefficient at a specific level are replaced with the bits of the secret data. For instance, if the next bit is secret message is 1, the LSB of the coefficient might be incremented by 1. If it's 0, it might be decremented by 1. So, the third point is extraction. To retrieve the hidden information, the recipient applies the reverse process. They transform the steganographic image using DWT and then extract the LSB of the wavelet coefficient at the specific level where information was embedded. And the last method is DFT, discrete Fourier transform. In this context of DFT steganography, the cover object is typically an image or audio signals, and the hidden message is often a piece of text, image, or some other data. This method is mathematical transform that converts a signal from its time or spatial domain representation into its frequency domain representation. These can help separate the signals into different frequency components. Let's take an overview of how DFT steganography might work. The step 1, transform the cover object. Apply the DFT to the cover object or file, image or a audio signal to convert it from its spatial domain to the frequency domain. The second step, manipulate frequency components. Modify the amplitude or a phase of certain frequency component in the DFT representation of the cover object. The choice of which component to modify depends on the algorithm of steganography which we are using. The changes should be subtle enough to avoid noticeable alteration to the cover object. The third point is embed the hidden message. Encode the hidden message within the modified frequency component. These could involve altering the least significant bit of the coefficient to accommodate the hidden data. Since the human perceptual system is more sensitive to changes in lower frequency component, embedded data in higher frequency component might be less noticeable. DFT steganography can be more robust against certain types of attacks compared to spatial domain techniques, since the frequency domain representation can tolerate some amount of changes without visibly altering the cover object. So let us discuss about steganography tools. The steganography tools are specialized software designed to facilitate the embedding and extraction of hidden data within digital files or images. This tool provides a user-friendly interface for individuals seeking to utilize steganography techniques for various purposes. These tools can be broadly divided into two categories. The first category is GUI tools, means graphical user interface tools. These tools offers a user-friendly interface that requires minimum technical expertise. User can easily load these cover media, images, audio, video files, specify the hidden data and applying the steganography techniques through simple interaction. The popular examples include OpenStago, StagHide and Quick Stago is a popular tool for steganography. The second category is command line tools. These tools are more suited for user comfortable with the command line interface. They provide greater control for flexibility over the steganography process, allowing user to fine-tune parameters. Some examples of these category tool is Outguesses, Stago and LSB Stag. So everyone keep in mind that successful steganography involves finding a balance between amount of hidden data and the visual impact on the cover images. If the change are too significant, the steganography may be easily detectable. Conversely, if the changes are too subtle, the hidden data might be lost due to compression or image alteration. It's important to note that the field of steganography is vast and constantly evolving. Researchers are continuously developing new techniques, and the effectiveness of any specific method can depend on the factors like the sophistication of detection tools and perceptual limitations of human senses. Thank you for joining today's lecture on the fascinating world of steganography. the art of hidden message in plain sight. And looking forward to seeing you in the next video or whenever you need support. Have a great day. Goodbye.